All right, let's get started. You guys are all excited about main memory, right? Some more reminders about assignments. We'll talk about the assignments that you're doing, but how many people are done with Lab 5? That's it? How many people are still doing Lab 5? That's good. You have late days, right? That's good. But Lab 6 is coming up too, so you guys should get started. I told you that it's going to be hectic toward the end of the semester, but you'll learn a lot, so don't worry. Again, in the end, what matters is learning. Homework 5 is due March 29th. We extend the deadline a little bit, I think, for 2 days. It'll be out later today. Actually, it may already be out, right, if you've incorporated everything. OK, not yet. And then midterm 2 will be coming up. That's going to be toward the end of the semester. So we'll talk about the dates at some point. So the course, we have 1.5 months left, and the course will move quickly in the last 1.5 months. That's true of all courses, unfortunately. Wish we had a little bit more time in the semester to actually cover all of the concepts. But please manage your time well and get help from the TAs. TAs are here during office hours and recitation sessions to help you. This is the key in the end. This is what will matter in the long run. OK, one thing that I will suggest you attend if you're interested in looking at these. I don't have the time for this, but I believe it's 4:30 or 4 p.m. There's an upcoming seminar on flash memory. Unfortunately, we won't have time to cover flash memory, at least in some detail, in this course. But this is my PhD student, Yishin Luo, who will actually present a paper on data retention in multi-level cell NAND flash memory. He'll present a characterization of the retention behavior, how long data gets retained, and what happens while data resides in flash memory without being touched. And he'll propose some mechanisms to optimize it, and he'll propose some mechanisms to recover data even after the lifetime of flash ends. So this should be an interesting talk. This was one of the reasons why I was actually absent in one of the weeks during the semester, if you remember, and it was presented the best paper session. Yes?
What time is that?
What time is it? Is it 4 p.m., Rachada? 4:30 or can you check quickly? Or we can actually do this. Let's do it. 4 to 5? OK. You can actually find it on this website, too. Yeah, 4 to 5 p.m. There you go. So I would suggest that you attend this. It'll be fun. This is something we won't cover. OK. But we will cover DRAM, which also has retention issues, as you know. And these are some of the seminars. There will be some seminars relevant to many topics covered in 447. This semester and later semesters also. So even if you cannot make it this semester, I would suggest that you subscribe to this seminar list. And you can find this if you search for Calcium seminars. Calcium stands for Computer Architecture Lab at Carnegie Mellon. You can actually join the lists. And I'll tell you more about the relevant seminars when they come up. You probably are all waiting for this, right? I'm not going to ask how did the midterm go because we already graded it. I think I have a good idea of how it went. Could have been better, of course, but hopefully this is your first experience with a 447 midterm. There will be 2 more, hopefully. So this is the statistics. You can find your own score. This is the grade distribution in terms of percentage. And this is in terms of absolute values. The total was 340. And it's actually not a bad distribution. So if you're below this point, you should really study harder. Or maybe below this point. OK? And the solutions are online. Yes?
What do the bins actually represent? What's the range on each one?
So this is, I believe these are the scores between 120 and 160. And these are the scores between 240 and 280. OK? But you'll get your exact score. It's online. And you can see the grade breakdowns per question as well. It's actually interesting to look at. If a question is particularly not well done, it may reappear in the future. OK, so going forward, as I mentioned, what really matters is learning in the end and using the knowledge, skills, and ability to process information in the future. So I would still like to say focus less on grades and put more weight into understanding, because that's what will matter in the end. And even if you didn't do too well in midterm 1, actually there are a lot of you who did really well. Midterm 1 is only 12% of your entire course grade. So keep that in mind. In a sense, it's worth less than 2 labs plus extra credit. And we have a lot of extra credit opportunities. And there's still midterm 2, final, 3 labs, and 3 homeworks. And there are many extra credit opportunities. So it's great for learning by exploring your creativity. So I would suggest, many of you are focusing on extra credit actually, which is really great. I would suggest you continue focusing on this. So if you didn't do well on midterm 1, you can actually make up with the extra credits. Having said that, it's been a while since we recognized extra credits. This is for lab 3. I think this is number 5. Rohit? Is Rohit here? He's not here. OK, not today. But this is the percentage in the entire course grade that Rohit got, 2.25%. So he's already made up 1/6 of the midterm grade, if that's important. Terrence, he got 2.5. Jipang, there you go. And you actually, and Jipang and Junhan actually have the same critical path. And Brandon, he's not here. Well, I guess people who do not attend class do well. It's hard to conclude that. I had the exact critical paths. But these 3 are the designs that actually work 100%. I believe these 2 fail 1 test case, but we still decided to give extra credit. You're approximately correct and fast at the same time. OK? Any questions right now? We'll give out the exams later in the course, later today. Do you have them, Kevin? OK, great. Maybe during the break or after, at the end. At the end is probably better, so that you don't get distracted toward the latter half of the course lecture. So where we are in the lecture schedule, this is what we've covered in the memory hierarchy. Today we're going to focus on a really important part of the memory system, which is main memory, DRAM. Everything is really important over here, but DRAM is becoming even more important going into the future. And hopefully I'll tell you why. But we have some required reading. This is actually a paper that I've been wanting to write for a while. This is an overview of the issues that we have in the main memory system today that I've written with my students, 2 of my students. It's about 26 pages. That includes the references, though. Without the references, it's about 18 pages. So this will be your reading for the next few lectures. And it'll actually cover a lot of different ideas as well as a lot of different problems. So hopefully it'll be interesting. There are some more required readings. Basically, we'll talk a lot about DRAM organization operation. The basics are really covered in these 2 papers. By the way, the reason I'm assigning these papers is there is really no good, concise material that explains DRAM operation very well in literature today. That's why I'm assigning some sections of these papers. Sections 1 and 2, introduction and background of these 2 papers, which we'll also talk about later. And sections 1 and 2 of this paper that talks about to give you an idea of refresh. So, and some of you have already done this reading anyway. It was one of the readings that you could choose from in homework 1. OK. Why is memory so important? Before I go into DRAM in more detail, I'd like to give you some motivation on why we're going to focus a lot more on memory toward this second half of the lecture. We also already started it, but this is what we're going to talk about. This is basically the main memory system. It's a critical component of all computing systems that you design. Whatever system you design, you've got to have some kind of working storage. You can think of it as a working storage. And this system, if you would like to increase the computation capability, this system must also scale in many, many dimensions. In its size, its technology, how small you can make the cells, its efficiency, its cost, and in the algorithms that you use to manage it. It must scale if you want to maintain the performance growth that we are seeing on this side. So Moore's law, if you remember, really talks about the processors. but you would like to also scale main memory in the same way. This is another view of the main memory system. I think I've shown you this picture a while back, maybe in the first lecture. But if you look at a chip today, this is a cartoonish picture. The computation is really confined to these red parts. Everything else is really moving data and storing data. And we've covered a lot of the caches over here. This time we'll focus on the memory controllers and the buses and the shared memory. So let me tell you a brief overview of the state of the main memory system today. There's some recent technology, architecture, and application trends that lead to some new requirements from the memory system, and that exacerbate some old requirements. Remember the old requirements? The ideal memory, zero cost, zero latency, infinite bandwidth. There was one more. I guess zero energy would be nice too, right? Infinite capacity. We still want those old requirements, but there are also some new requirements. And given these new trends, DRAM and memory controllers, as we know them and as we design them today, are already unlikely to satisfy all of these requirements. And there are also some emerging technologies that we will talk about later that enable new opportunities that can potentially solve these new requirements. And we'll talk about that toward the end of the class. One example is phase change memory. So given this, we're at a point in computer architecture where people are already rethinking or reinventing the main memory system, because things are not scaling as well. To fix the issues that we're having with DRAM, and one of which you're already familiar with, I'll repeat that again, and enable some of these emerging technologies while satisfying all of these requirements. So let's take a look at some of these requirements that are relatively recent that have been affecting main memory. First of all, there's an increasing need for main memory capacity, bandwidth, and quality of service. And you're already familiar with many of this. The second is main memory energy and power is a key system design concern today. And third thing is DRAM technology scaling is ending. Let's examine these in a little bit more detail. So why do we, this slide says capacity actually, but you can actually say demand for memory, more memory capacity, bandwidth, as well as quality of service. In most systems, as you scale the computation capability, we're adding more cores, which lead to more concurrency and a larger working set. And these are actually old slides, as you can see over here, right? We're well beyond 8 cores today. And this was a prototype at that point. But if you look at a GPU, for example, it has lots and lots of cores. Thing I cannot count. And modern applications also at the same time. So we're on the architecture side, we're adding more computation capability, which requires larger working sets, which requires more bandwidth, more capacity, as well as more quality of service, because these things interfere with each other, right? Also, we're at a point in systems today where applications are increasingly data intensive. I don't recall any point in human history where we demanded so much data, right? If you look today, for example, in genomics, we can sequence a human's genome very, very quickly today. The problem becomes, how do you actually analyze that huge genome? How do you actually map it to a reference genome? And how do you actually figure out what vulnerabilities this person has, what kind of interactions this person will have with different drugs, right? So that's all about processing data. And because these kind of interesting applications have appeared, and they've appeared because the cores have scaled, actually, because the computation has become cheap, memory has become a bigger bottleneck. And finally, there are many applications and virtual machines that are sharing main memory. So if you look at cloud computing and servers, people would like to consolidate more and more applications such that you can improve efficiency. If you look at GPUs or heterogeneous computing, there will be many threads from multiple applications. And you can already see that in CPU-GPU integration in systems today. Actually, there are systems that integrate FPGAs also at the same time today that you can buy. And if you look at mobile systems, there's a lot of consolidation that's happening here. So many applications are actually already sharing this main memory. In fact, main memory is one of the most important resources in this kind of system because you have a lot of different accelerators sharing the main memory as well. And you can actually add ... over here. So this is one slide, one example that's showing the memory capacity gap. This is a slide from ISCA 2009. I don't have the reference over here, but it was a paper written by HP Labs. What they did was they plotted the core count. It's doubling approximately every 2 years. It's this one over here. And they plotted the DRAM DIMM capacity. It's doubling approximately every 3 years, which means that if you make the calculation, if you do the calculation, memory capacity per core is expected to drop by 30% every 2 years. Now, if you have a single-threaded application, what you see is 30% reduction in memory capacity, assuming you're all running single-threaded application in the different cores, which is a bad thing because the software is actually relying on more memory capacity coming up, right? You're actually writing the software, adding more features into the software, which is consuming more memory. So this is bad. This is making programmers' life harder in the end. And if you actually, this may be a good bonus question for a homework. If you plot the trends for memory bandwidth per core, they're much, much worse. Memory bandwidth is increasing by about 10% per year. It's not really doubling every 3 years. OK? OK. So we need more memory capacity, bandwidth, as well as quality of service. We'll get back to quality of service, but quality of service we already talked about, right? If you're adding more applications or more threads sharing main memory, they're interfering with each other. The second major trend that's relatively new is energy and power has become a key system design concern today, which was not true maybe 20 years ago, or maybe even 15 years ago, right? People were designing systems mainly for performance, much less so for energy. And memory actually consumes a lot of the entire system energy. This is a relatively old data point. It's actually a nice paper in IEEE Computer written by researchers at IBM Research. What they found out that after analyzing big iron machines from IBM, big data centers at that time, is 50% of the entire system energy is spent on the off-chip main memory hierarchy. It's a lot, right? It's approximately 50%. And similar results exist for this kind of systems also. And one issue with DRAM is it consumes power when it's idle. It requires periodic refresh, which is also a bottleneck, as we've discussed earlier. On top of this, the third problem, DRAM technology scaling is ending at the same time. And you've seen already evidence of this. I'll repeat this, right? Remember the row hammer problem in the first lecture, 20 lectures ago? That's actually an example showing that DRAM technology scaling has become really difficult. And we've discussed technology scaling. Basically, we're reducing the size of the DRAM cell. And that has enabled a lot of benefits. It has enabled higher capacity, lower cost, higher density, and reasonable energy scaling. The problem is, as you reduce the size of that cell to become smaller, it becomes less reliable. And ITRS, International Technology Roadmap of Semiconductors, it's a consortium that basically roadmaps what's going to happen to semiconductors into the future. They've been projecting that DRAM will not scale easily below X nanometers. And X varies depending on the year of their report. But it's clear that as you reduce X to a small value, it's becoming more costly to reduce the size of these cells. So let me tell you a little bit about the DRAM scaling problem. And you already know this, that DRAM stores charge in a capacitor. It's really charge-based memory. This capacitor must be large enough for reliable sensing. And this access transistor should be large enough for low leakage and high retention time, because this capacitor actually leaks through this RC path. That's why you need to refresh it. And if this capacitor is too small, it actually becomes more vulnerable to reliability issues. It becomes more vulnerable to noise. And it becomes more leaky also. So as you reduce the size of these both, that's how you can actually get more capacity in main memory. Both of these properties become much harder to maintain. The capacitor becomes less reliable, and this access transistor becomes also less reliable and more leaky. And things become closer to each other, right? As a result, you become more vulnerable to disturbance. And this was actually the value that was assigned to X by ITRS in 2009. They said scaling beyond 35 nanometers is challenging. Can anybody guess what is the feature size that we have today in DRAM? Say it again?
Below 35 nanometers.
You're right, below 35 nanometers. This was 2009, right? Today it's about 20, yeah.
Is it 22?
22, that's right, yes. Today it's about 22, and 20 is coming up going forward. But it has come at a cost, right? And you already know this. You've already seen this slide. Basically, in many chips that exist today, if you activate a row repeatedly, activate precharge, activate precharge, activate precharge, you can actually cause disturbance errors on rows that are adjacent, but logically totally unrelated to this row. And you've read this paper. Some of you have read this paper, but we've already covered this. This is basically disturbance errors. And this is an evidence of the DRAM scaling problem. And I've already given you this data. These are 3 different DRAM companies, and most of the DIMMs that were manufactured that my students have tested are vulnerable to this kind of errors. And you can actually take advantage of this, right? How many of you have tried this program? None? Well, you were too busy doing your assignments, I guess. Basically, you can download this program from my group's website and actually test it. And this is actually a real reliability issue, and it's been happening recently. So it wasn't observed until 2010, and it has happened in all of the chips that were tested that were manufactured between 2012 and 2013. Well, why is it happening? Because this is really a scaling issue. As you reduce the size of the cells, they become more vulnerable to disturbance, right? It wasn't happening before because it was easier for the DRAM manufacturers to contain this kind of errors. They could test for it. Maybe they didn't even need to test for it because this disturbance was not as big of a deal, right? The disturbance happens because you keep activating a row over and over, and this caused accelerated charge leakage in the cells around that row. And if you don't refresh it frequently enough, you'll lose the data in the cells around. Does that make sense? And this is actually very, very fundamental to many memory technologies. Flash memory has a similar error mechanism. Hard disks have similar error mechanisms. If you read the paper, you'll actually figure that out. So it's really nothing new at the higher level, if you will. But it's becoming a bigger problem because now it's being exposed to the user, right? If you have this kind of errors, then your programs will be incorrect because this is your main memory. And most of the systems today don't use error correction, right? For example, this one has no error correction in memory. This one has no error correction in memory. Only server systems use error correction because error correction adds more cost. If you had one more lecture, we would dedicate it to error correction probably. OK, so this has security implications. This is to motivate why this is such an important problem. So if you look at the paper, and many of you have read the paper, what we've written was memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other accesses. In fact, if you're following the news, Google has taken and read this paper and taken the code that my students have written, and they've used it to gain kernel privileges in systems. So you can take a look at this website. They refer to the paper. Basically, I'll briefly read this because I think this kind of issues will become even more important going forward. They say row hammer is a problem with some recent DRAM devices in which repeatedly accessing a row of memory can cause bit flips in adjacent rows. We tested a selection of laptops and found that a subset of them exhibited the problem. This is the Google Zero project. We built 2 working privilege escalation exploits that use this effect. And now that you know virtual memory, you'll perhaps understand. One exploit used row hammer-induced bit flips to gain kernel privileges on Linux when run as an unprivileged user process. When run on a machine vulnerable to the row hammer problem, the process was able to induce bit flips and page table entries. It was able to use this to gain write access to its own page table, and hence gain read-write access to all of physical memory. It's kind of a cool attack, right? You can actually, I don't know if they made the entire code available, but you can go to that website and you can take a look. So this tells you these are actually serious problems. If you cannot correct these problems, you can actually take over systems. And it's going to have very wide-ranging implications as you can imagine. I find this pretty cool. Who finds this cool? Good. So the goal is to fix it, basically. Let me give you another perspective. This is kind of the perspective from the high level, right? If you have this kind of errors happening because the memory is not scaling, if you cannot fix them, maybe there are a lot of security issues, and maybe the systems are broken, right? But there's also the low-level problem, which is, I don't remember if I mentioned this paper in the first lecture, but this is a paper written by Samsung and Intel together, again last year in 2014. They basically identify 3 things as the main process scaling challenges of DRAM. As you reduce the size of the circuit, you need to refresh it potentially more frequently. Refresh becomes a much bigger problem. And it's because it's difficult to build high aspect ratio cell capacitors, decreasing cell capacitance, right? And the leakage of the access transistor is increasing. This is what I told you before. And you become more vulnerable to this VRT problem. I mentioned this briefly. Basically, it becomes difficult to determine the refresh rate for a DRAM chip because DRAM cells have this weird behavior where their retention time changes randomly. It's like quantum-like effects in DRAM, if you will. Basically, for a while, a cell can retain data for seconds, let's say, and then it jumps to a state. Charge gets trapped in the access transistor, and it jumps to a much leakier state where it retains data only for, let's say, 32 milliseconds. That's the VRT problem, variable retention time. And as the cell capacitance decreases, basically the capacitor becomes smaller, this becomes much more of a bigger problem. And this is said by Samsung, which is basically one of the major memory manufacturers. So the major memory manufacturers are also admitting that DRAM is becoming much more difficult to scale. So you're actually studying computer architecture at a time when memory is facing a lot of problems. And if you're interested in this, I'm going to skip the TWR. Write latency is also increasing, but I believe this is a less fundamental problem than refresh and variable retention time. So if you want to learn more, you can take a look at this paper that's written by Samsung and Intel together. Right? Samsung and Intel, it's kind of weird that they write papers together. But they also realize that this is a problem, and maybe you need to solve the problem by taking a look at controllers and DRAM together, somehow designing DRAM and controllers together. Does this remind you of something? Hard disks, flash memory. If you think of hard disks and flash memory, they don't come just by themselves, right? I mean, they do, I guess, but hard disks come with a controller together, right? The controller actually manages the errors. Flash memory also comes in an SSD, and the flash controller actually manages those errors. Well, DRAM, today it doesn't come with a controller. Controller is part of the processor, right? Well, maybe going forward, DRAM will come with a controller also, and controller will manage all of these issues. Anyway, hopefully this gives you some perspective about the issues that we're seeing with main memory. And that's why it becomes important, much more important to study it today. And there's also this orthogonal issue. This is really orthogonal to the DRAM scaling problem. If you're actually adding more cores, more agents that are accessing main memory, they interfere with each other when accessing this main memory. And uncontrolled interference, as you know, leads to many problems, as we've discussed. Quality of service problems, performance problems, predictability problems. And we're going to get back to this. So to recap, there are some relatively new major trends affecting main memory. We want more capacity, more bandwidth, more quality of service, more predictability. Energy and power is increasingly more important. And DRAM technology scaling is ending. And it will not become easier, basically. It's clear that manufacturers will try to scale DRAM to smaller size, but they will see more and more issues like the Roheimer problem, because it's just fundamental. As you push the circuits down that much, they become more vulnerable to errors, and you need to find ways to fix them. OK, so hopefully this gives you an idea of the perspective that we have today in memory. So I'll cover the basics. How can we fix the memory problem and design memory systems for the future? Well, as an architect, you've got to understand it first, right? Which means that you've got to look backward to actually look forward. We first need to understand the principles of memory and DRAM, what this lecture will be about, and the memory controllers. If you don't understand these, how are you going to design the memory controllers of the future, right? And techniques for reducing and tolerating memory latency. I didn't talk about latency as much, but latency is also becoming much more important going forward. And potential memory technologies that can compete with DRAM going forward. This kind of thing may not have been that interesting to examine 10 years ago, right? Because DRAM was scaling really nicely. But today, we're at a point where in an introductory computer architecture course, we should really look at what are these technologies that are coming up. Because you may actually end up designing things for it in 5 years, sooner than you think. OK, so this is what we will cover in the next few lectures. Let's first start with main memory. Any questions so far? OK, this is exciting? Yeah? If not, it will be. OK, so what we'll talk about is this. Again, this is the AMD Barcelona I've shown you before. We've covered cores. We've covered caches. We haven't covered the interconnect, but we will get to it. We will cover the memory controllers and the DRAM banks and a little bit of the DRAM interface. But we'll start with this part of memory. If you think of memory, I'm going to use my nicely hand-drawn pictures. And we can switch to that when needed. But this is at the most abstract level. Memory looks like this, right? You get an address, and you get some data. And you have 2 to the n locations, and each location gives you k bits. And you can have a write enable, and you can have a chip enable. Chip enable is basically, this is the memory enable signal, right? If you remember from LC3B. And actually, this is the high level of memory. If you look into smaller portions of memory, memory consists of things that look like this, that are regularly laid out. And hopefully, I'll give you a perspective of that. And this is a memory bank. You can see the memory bank looks exactly like this, right? Well, maybe I omitted the enable signals over here. OK, I'm going to skip these because we've already reviewed what SRAM and DRAM looks like. And we know the difference between DRAM and SRAM. Let's cover some fundamental concepts. You already know many of these. But physical address space, this is the maximum size of main memory, right? Total number of uniquely identifiable locations. It's different from virtual address space that we've covered. Physical addressability, this is the minimum size of data in memory that can be addressed. Right? You could have byte addressable memory, word addressable memory, 64-bit addressable memory. Again, this is different from the ISA addressability, right? Because ISA can have a load instruction that loads a word. But at the physical level, your cache may be different, right? At some point, you need to supply that word to ensure that you obey the ISA. But your memory can give you 4 kilobytes, right? The addressability can be 4 kilobytes, and then you pick the word at the physical level. Basically, the microarchitectural addressability, physical addressability, depends on the abstraction level of the implementation. What does this mean? Well, what I said before. Basically, at the cache level, you may be able to access a word at one cache level. But the L2 cache level, maybe you just get a cache block, right? Maybe you just get a cache sub-block. At the DRAM subarray level, maybe you get the entire 4 kilobytes first. In fact, you cannot access a DRAM subarray. We'll get to DRAM subarrays in a little bit. But if you cannot access a DRAM subarray, you cannot just get a bit from DRAM. And we've seen this before, right? You activate an entire row. An entire row could be 8 kilobytes, let's say. OK? And then you pick the words later on in the system. So physical addressability is very different from the addressability that's visible to the programmer. Alignment. Does the hardware support unaligned access transparently to software? We'll not cover this as much, but you know the alignment from MIPS. And interleaving, you already know this concept very well. It's banking, right? So I motivated interleaving in 2 different ways, if you remember. Basically, interleaving is the same as banking. And we motivated, one way we motivated is we want to have multiple accesses to memory, right? We want to have high bandwidth memories. So why don't we bank the memory such that we can start access to one bank and overlap it with another access to the other bank? Assuming accesses go to different banks, you can actually get the data in a pipeline manner from the banks. But you can also think about this from the physical perspective. Basically, if you design memory as a single monolithic array, it takes long to access, right? It's a lot shorter to access a smaller array. I guess I'll demonstrate this very quickly. I guess I need to do this. Oh. Did we rotate 3 times? 1, 2, 3. There you go. So if you have a memory array that looks like this, basically you input an address, and you need to determine the row, right? You have a row decoder, and then you have a column mux over here. And let's say you have n bits over here. If you have a single monolithic array, it takes much longer to access this array because you need to drive these long bit lines now. Whereas if you chop it up to smaller pieces over here, let's say 4 of these, you have 2 to the n divided by 4, right, in each of these. And you can actually have separate row decoders and column decoders over here. That's the concept of banking over here. This is slower to access. This is much faster to access because you're driving much shorter wires over here. And you can think of this as in the x dimension as well. You can chop it up in the x dimension too. And then what you will get is something like this. Does that make sense? So instead of having a single monolithic array, we have multiple, I'll call it banked arrays. OK? That's one other reason for doing interleaving or banking, such that you can reduce the latency of a memory array access. This, at the same time, enables parallel accesses to these smaller arrays, right? Now you can exploit the parallelism, because you actually have separate decoders, hopefully, for these. So that's the idea of banking. Divide the array into multiple banks that can be accessed independently, or mostly independently, in the same cycle or in consecutive cycles. In this case, each bank is smaller than the entire memory storage, and hopefully access to different banks can be overlapped. Because you can start, well, as you've seen before, you can start this access, and then you can start this access over here, and then you can start the access over here, and then over here, as long as accesses don't conflict with each other, right? In fact, this also gives you another perspective, right? You remember that I showed you this picture over here. All memory looks like this. Well, this one looks like that, and each of these look like that, right? In fact, if you want to reduce latency even further, what you do is you divide this into subarrays that look internally. It's like the snowflakes. Regardless of however you zoom in, they all look the same. OK. So that's the idea of banking. And you already know this idea of banking. So a key issue in banking is, how do you map data to different banks? And we kind of covered this earlier. I'll cover this in a little bit more today. Basically, the other way of asking this question is, how do you actually interleave the data across banks? Here's one example over here. Basically, assume each bank supplies a word over here, and we have two banks. The key question in interleaving is, which banks do consecutive words in memory get mapped to? Right? You can have a single word mapped to here, the next word over here, the next word here, the next word here, the next word here, dot, dot, dot. That's kind of word interleaving, right? You can have a cache block mapped here, the next cache block mapped here. That's cache block interleaving. You can have a row or page, an entire OS page, mapped to this bank, the next page mapped to this bank, the next page to this bank. That's page level interleaving. Now you can actually think about different granularities. You can think about all the top half of the memory address space mapped to this bank, and the bottom half mapped to this bank, right? That's kind of bank granularity interleaving, if you will. OK? And this is kind of a nice way of looking at the bank, right? Basically, these are two banks that actually share the address, command, and data buses. Only one bank can load the data bus at a given time, but you can pipeline the accesses. This is what we had seen when we talked about GPUs, for example, when we talk about vector processors. So there are many interleaving options, and I'll let you think about these a little bit. This is basically, let's assume that this is your physical address. You have 13 bits. And this is one interleaving scheme. And in this case, basically, you're really interleaving at the word level, OK? Because you're actually taking 2 bits. You're using this bit to actually decide which bank, assuming you have 2 banks. If you do this, this is interleaving scheme 2. What I discussed the last, basically, half of memory is mapped to bank 0. The top half is mapped to bank 0. The bottom half mapped to bank 1. Right? And this is kind of you're selecting the bank bits somewhere in the middle. So it's another way of doing interleaving. You can actually select your bit from anywhere, right? It doesn't matter. OK, but it does matter in terms of the access patterns. Basically, for example, if here you may get a lot of conflicts in the same bank, assuming you're actually using most of your address bits start with 0, right? The addresses you're accessing all start with 0. They're all mapped to bank 0, right? That's maybe a bad idea. Usually, what the bank bits come from the bottom bits because they change more frequently. In other words, there's more entropy in the bits that are lower than the ones that are higher. Right? OK, but we'll get back to this. OK, so you remember that Cray 1 had 16 banks, right? And we had 11 cycle bank latency in Cray 1. And they mapped consecutive words in memory into consecutive banks. They used word interleaving. And they could start one access per cycle. Well, you already know the answer to this, right? Can banks be operated fully in parallel? Sure. You just need to have separate address, data, and command buses to the banks. Not these banks, because these share the data bus, so they're not fully in parallel. They cannot supply the data at the same time. Well, they could, I guess, but you get garbage in that case. So the cost of this is, we've seen it earlier, actually. Remember when we talked about high bandwidth memories? You can actually have true multiporting, for example. Or you can actually duplicate and have two totally separate banks, right? So the cost of this is relatively high. If you look at modern processors, they have L1 data caches with multiple fully independent banks, whereas DRAM banks actually share the buses, address, command, and data buses. DRAM banks look much more like this one. Whereas if you look at an L1 cache, they're relatively independent banks. Well, they don't share the, they actually do not share the, this part, the data bus. They can supply data independently because you have multiple load ports, right? You want to get the data to both of the loads at the same time. You don't want to pipeline them. Otherwise, you're not able to issue 2 loads per cycle. OK. So the bank abstraction, let's take a look at the bank abstraction. Well, this is the same thing I told you. All memory looks the same. This is bank 0, let's say. And 1K rows is actually just a made-up number to make the numbers work in the previous example. Today, if you look at a bank, it's about 32K rows or so, where each row is about maybe 4 kilobits or 8 kilobits. But even this is an abstraction, actually. Basically, think about a chip that you're getting 32 bits in one access. Basically, the 32 bits, you don't actually get the 32 bits from one chip. They actually can come from multiple different chips, each of which can supply 32 divided by n bits. So it kind of looks like this. I'll introduce the term rank now. Basically, this is your bank 0. Instead of having a bank give you 32 bits, you actually have multiple chips, each of which give you 8 bits. And you aggregate them and get the 32 bits that you need. And imagine these to be different chips. And this is called a rank. So each chip, let's say, has multiple banks. But we're looking at bank 0 over here. And a set of chips that respond to the same command and same address at the same time with different pieces of requested data is called a rank. Does that make sense? Well, why would you want to do this, right? Why not build a chip that looks like this, that supplies 32 bits right away? You could. There's no reason you cannot. Except today's DRAM is not designed that way because it's a lot cheaper. Remember the pins, right? These are actually data pins that are going out of the chip. Producing a chip that can give you 32 bits of data requires 32 data pins. Manufacturing a chip that gives you 8 bits of data requires only 8 pins. So this is much cheaper. Yes?
So
you have 4 of them. That's right. But each chip is hopefully much cheaper.
More than 4 times cheaper.
That's right, yes.
So why stop there?
Yeah, you could. So there's a trade-off point, obviously, right? you can talk with the DRAM manufacturer. Why stop there is a really good question. And how does this affect the entire system cost, right? That's also debatable, right? But DRAM is optimized this way today because that pins are limited. That's true for the processors as well, actually. Adding more channels is much more difficult today because it requires more data pins, right? That's why memory bandwidth is not scaling as well. Otherwise, you would end up many channels. You would add many channels on a chip, right? And also think about another way. Well, eventually you become area limited, right? Because these I/O pads that you require to actually add more pins are relatively large and they occupy a lot of area. And you have only so much chip space. OK? I'm not saying 8 is the right answer. But this is done because to minimize the pin cost. So that's the idea, basically. And this is the idea of a rank. So this tells you that even this bank is really an abstraction, right? Underneath, it's really, the data comes from different chips. And if you want to actually think about this as a chip, this is bank 0. But there's also bank 1 in this chip. There's also bank 2 in this chip. And there's also bank 3 in this chip. Does that make sense? We'll see this in a little bit. OK, so let's go into a little bit more detail. We've kind of given you the basics in terms of what a bank is and what a rank is and what a chip is. But if you think about the DRAM subsystem, you can think about it in two different ways, from the bottom up and from the top down. I'll go from the bottom up first. Basically, we start with a DRAM cell that I showed you earlier. And then you actually have a two-dimensional array, which is rows and columns of cells. And that's what we will use to design a bank, basically. A DRAM bank is a two-dimensional array of cells, as we've discussed before, rows and columns. A DRAM row, unfortunately, is called a DRAM page. I don't like this terminology because we've used page in a different way, right, in virtual memory. But unfortunate. This has nothing to do with a page in virtual memory. And this is the reason why this is called page mode DRAM. Basically, you have this two-dimensional array of cells, and you have sense amplifiers over here. And we've seen the sense amplifiers before. These are basically cross-coupled inverters that take the data in a column and amplify it when they're enabled, right? Basically, you have word line, and you have many word lines. These are the rows. And you have many bit lines. These are the columns. To access a row, you activate the row, activate the word line. And the sense amplifiers amplify the data that's on the bit line over here. And then you figure out what the value is in that entire row over here. So that's how it works. So these sense amplifiers are also called the row buffer. Basically, once you amplify the data in that row, once you activate the row, you amplify the data. And the data in that row gets captured in these cross-coupled inverters, which are the sense amplifiers. So each address is really a row and column pair. And this is called page mode DRAM because you're really latching the row, if you will, inside this row buffer, right? And access to this row inside the row buffer is much faster than an access to a row that's not inside the row buffer. And we've seen this earlier, right? If you access to a closed row, a row that's not inside the row buffer at that point, a row that's not activated, you need to first activate it, right? It opens the row, and you do the sensing process, which places the data into the row buffer. And then you can issue read and write commands to read the column that's in the row buffer or to write into the column that's in the row buffer. OK? And once you're done with that access, you need to precharge the array. And the precharge command basically closes the row and prepares the bank for the next access. Basically, it precharges these bit lines such that the next access, next activate, can perturb the bit line such that you can sense it. Make sense? So in your basic circuits class, hopefully, you've learned about this. Who has? Some of you. OK. So that's why you need to do the required reading. That's a lower level abstraction. Take a look at the required readings. But this is the level of abstraction that you need to understand the rest of the lecture. Access to an open row, on the other hand, open row means you've already activated the row, and the data of the row is already in the sense amplifiers. When you need to access it, you don't need an activate command. The data is already there. So you basically issue a read and write and get the column that you need out of that. OK? But you still need to precharge it once you're done, if you want to access another row. So this is the DRAM bank structure in a little bit more detail. I'll show you a more scary figure later on. This is basically the DRAM bank array. And this is one example. You have 2 to the 14 rows over here, 2 to the 10 columns. This is a 2 to the 24 byte array. And this is a row address. This is a column address. And you mux out the column. And this is kind of the row buffer. Even though I show you a huge distance over here, these are actually really tightly coupled, tightly integrated. But basically, you can think of getting the data out as muxing out the column. And this goes out of the chip. This is the data out or in to or from the DRAM controller. And this is the address coming from the DRAM controller. And this is a command coming from the DRAM controller. This is kind of the boundary, basically. And a chip consists of multiple of these banks sharing address, data, and command buses, and a bunch of other circuitry over here. Okay? So DRAM bank operation, this is what we covered in the first lecture also, but let me go over this again. This is a two-dimensional array of cells. This is a row buffer, sense amplifiers. Initially, this is empty. Let's assume the sequence of accesses. You access row 0, column 0. Here, this is empty, so the DRAM controller first needs to send an activate command, and activate row address 0, which basically puts a high voltage onto the word line over here in address 0, which connects the bit lines of that row to the sense amplifiers, and the sense amplifiers actually sense the data because the charge gets perturbed. What does it mean to connect a cell to the bit line? Basically, the capacitor gets connected to the bit line, so the capacitor actually perturbs the charge on the bit line, right? And what the sense amplifier does is it senses that difference, and it amplifies that difference because it's really that cross-coupled inverter that can do that amplification. Okay? That's how you actually sense the data. And now you have the bits stored in the row buffer. So row 0 is in the row buffer now. Now the memory controller can send a read command to column address 0. And this basically, what this accomplishes is DRAM chip response with column 0 and sends it back through the data bus. In today's DRAM, these commands and data have associated timing constraints. Basically, the DRAM interface, DDR interface, specifies after an activate command, I don't know, maybe 5 DRAM clock cycles later, you will get the data into the row buffer. And you're guaranteed to do that. So the memory controllers are designed such that they know these latencies, and they can issue the next command based on when the previous command finishes. Okay? So if you want to access after this row 0, column 1, it's easier, right? Because the row 0 is already open, and memory controller keeps track of this information. What row is open in which bank? So the memory controller can tell that this row buffer hit. So it doesn't need to activate the row again. So it just sends the column address. It just sends this read command to DRAM with the column address. And the DRAM responds with the data at that column. If the next access is to column 85, again, the memory controller can check, oh, this is actually a hit in the row buffer. So you can think of row buffer as a cache, right? It is really a cache at some abstraction level. So this is, again, a hit in the row buffer. And the memory controller only needs to send the read command. And DRAM responds with the data. But if you want to access row 1, column 0, now the memory controller can check what is cached in the row buffer. And it sees that it's row 0, but it needs to activate row 1 in the same bank. So what the memory controller needs to do is first send a pre-charge command. It realizes that it's a row conflict. It first sends a pre-charge command to that bank, which basically pre-charges the bit lines, as I told you. It really pre-charges that to a particular voltage level, VDD over 2, such that the later activate can actually perturb that, and you can actually sense that difference. And after that, once the pre-charge is done, there's a latency associated with the pre-charge command. After that many cycles, the memory controller can activate row 1, which brings the data into the sense amplifiers. And then the memory controller can send the read command to the bank to get the data. Make sense? So actually pretty simple. Yes?
Is the pre-charging also writing back the row, or is it just getting rid of the row?
So you can think of it as writing back. At some level of abstraction, it is really writing back. But if you think about it at the very low level, at the circuit level, what's really happening is it's really disconnecting the cells, the row, from the bit lines, right? And then changing the bit line voltage level. But at a level of abstraction, it's really writing back. Okay? But the circuit level, it's already, what happens is that while the sense amplifier is connected to the cell, they're all at the same voltage level. Right? You're just disconnecting it to change the voltage level of the bit line. Okay? Yes?
When you change a value in the row buffer, even before you write it back, it's already changed.
Exactly. Yes. Exactly. Yeah. So that's a very good way of thinking of it. Of course, you need to wait until that write takes effect. Right? There's a write latency. It's called the write recovery penalty to ensure that everything gets propagated into the cell. Okay. Okay. So the DRAM chip. This is a single bank. Remember, a DRAM chip consists of multiple banks, and 8 is a common number today. Banks shared command address and data buses. And the chip itself, as I told you before, has a narrow interface. You can read 4 or 16 bits of data. And changing the number of banks, the size of the interface, and whether or not command address and data buses are shared has significant impact on DRAM system costs, which we're not going to cover. But here's one example. It's actually a relatively old example. I think this is a 1 megabit DRAM chip. And this is exactly what I've shown you earlier, right? You basically get the address. This is the address bus. It gets registered. And it could be a row address or it could be a column address, depending on the command, right? And you latch the row address or the column address. And if you look at it, even the address is shared. You first supply the row address and you then supply the column address. Why so? Why not send the entire address? And then they get latched to the row and column. Same reason, right? Pins. Basically, here you need only, I don't know, well, there's a bank address also, but you need only 14 bits for the row address and the column address together. Whereas if you needed to send both of them at the same time, you needed 24 bits, right? 24 pins. Modern DRAM, you actually need to pipeline the sending of the row address and the column address. And you also don't need the column address for a while, right? Because you need to first activate the row if you want to access that row. So you can actually pipeline the sending of the row and column addresses. It saves pins. You also need to send the bank address. In this case, we have 8 banks over here, as you can see. So you basically have 8 row address latches and 8 decoders over here. And this is the memory array size, as you can see. And you can see the SEMS amplifiers in the bank. OK? And if you look at it, this is basically the row size is 8 kilobits over here, 8,192. And there's some other logic, and this is the column decoder. Basically, you can get the data out, and you're getting 32 bits of data over here. So what this DRAM is doing actually internally prefetching. Because the output is 8 bits, but the data that you're getting out of the column is really 32 bits. So what it does is it really stores these 32 bits over here. So you've actually essentially prefetched 24 bits. And you supply only one of those 8 bits out, column 0 and column 1. You can see that 2 address bits actually are selecting one of those. So internally, DRAM actually employs prefetching to ensure that you get enough bandwidth out of the chip. And you don't need to worry about this mess over here. But all DRAM needs to have that, actually. OK? OK. So let's go to the DRAM rank and module. Rank, as we've discussed before, it's multiple chips operated together to form a wide interface. And this is called a rank because it's really the same as a rank of soldiers, right? You give a command to a rank of soldiers, they all do the same thing, right? Hopefully. DRAM chips are hopefully more predictable than humans. All chips comprising a rank are controlled at the same time. They respond to a single command. They share address and command buses, but provide different data, basically. And we know the reason for this, right? Basically, this way you can manufacture the chip to be much cheaper. A DRAM module consists of one or more ranks. For example, dual inline memory module. This is what you plug into your motherboard, basically. And if you have chips with 8-bit interface to read 8 bytes in a single access, we use 8 chips in a DIMM, right? That's how you get 64 bits in a single access. Okay? And if you do 8 accesses, you'll get 64 bytes, which is a cache line in many systems today, cache block. And this is a pictorial example of a DIMM. Basically, you have 8 DRAM chips over here. They share the command buses, but they provide different data. Okay? So this kind of shows the sharing of the command buses. If you actually have ECC, error correcting codes, normally what happens is you have a DIMM with 9 chips. And the 9th chip actually stores the error correcting codes. Well, we won't cover that. So this is another look at the DIMM. Basically, this is the internal look. You have 8 chips over here. Each chip, if you go inside it, it has 8 of these banks. So bank 0 is really partitioned across 8 chips. Okay? So what is the advantage of having a DIMM? Well, I guess I've given you these. Basically, you get 2 things at the same time. You get a wide interface. You don't access only 8 bits, but you access 64 bits in this case. Hopefully, you get more bandwidth that way. But it also increases your capacity, right? You get both high bandwidth and high capacity. same time. It also gives you flexibility, in one sense at least. Memory controller does not need to deal with individual chips. It really deals with the 64-bit interface instead of dealing with every 8 bits. But there's also a disadvantage. Can anybody guess what that is? Of having this wider interface that you can only control in aggregate, not individual chips. You can only get 64 bits. What if you need only 8 bits, right? That's the problem with granularity, basically. Your interface is wider, but if all you need is just 8 bits, you just cannot get it. You have to get all of the 64 bits. So if you're doing only byte accesses to memory, you're really wasting a lot of energy, right? You're always getting 64 bits. And that's a problem with wider interfaces whenever you access a wider interface. You can actually make the same argument here, right? You have an entire row. If you want to get only, your goal is to do a load byte, and you're only reading that byte. But you're really activating an entire row of cells. That's a lot of energy, right? You're activating, let's say, 8 kilobytes to get 8 bytes. It's really waste. So it's really wasting a lot of your energy. But the reason it's done this way is because you need to actually have a memory array that operates that way, right? Alternative would be a memory array that kind of looks much more slim, right? This way. And your interface is just 8 bits. And you have a bigger row decoder over here, right? This way you won't waste a lot of energy, hopefully, because you're not activating an entire row of 8 kilobytes. But the problem is it's much harder to, it's much more costly to do this because the chip sizes don't look that way, right? You're really laying out things and you're really chopping up the chips. It's easier to manufacture things that are two-dimensional. Does that make sense? In fact, there are other latency things, latency effects that come into play if you want to design a bank that looks like this, because now your row decoder becomes much larger, assuming you want to preserve the same capacity. Okay? So this granularity will play a bigger role in the future. Yes?
Don't you generally access at least a cache block?
So that's a great question, right? If you generally access a cache block, then this is a good design. But even within a cache block, maybe you have that waste, right? Maybe cache block access may not be a good idea always. But you're right. So that solves. So if you're always accessing a cache block, this granularity is not a problem. But this granularity issue internally within the chip is still a problem, because even though you're getting only 64 bits, let's say, or 64 bytes, you're still activating an entire 8 kilobyte row. So that's in a sense harder to solve internally. Okay. Okay. So how do you get more capacity? Actually, why stop here, right? This is one DIMM. You can actually have more DIMMs. And in your system, you have slots for DIMMs, right? I don't know, how many maximum have you seen? Have you seen systems with 8 slots? 200 slots? Probably not, right? Yeah. So this is how you get more capacity in DRAM, basically. You add more DIMMs. Well, one way of getting more capacity is you increase the capacity of each DIMM. But there's limited capacity that you can get this way. Well, you add more DIMMs. This enables even higher capacity. The downside is, how do you actually interconnect this, right? How do you actually access these different DIMMs? Again, you need to address them somehow, and the memory controller controls it. And you need to somehow interconnect them. And you don't need to know about the topology over here. We'll get back to the interconnect. But this becomes more complicated. And the energy consumption can be high, because these are actually wires that are going through the board, right? And your scalability eventually becomes limited by the complexity of this interconnect and the energy consumption. That's one of the reasons it becomes more difficult to scale the size of the memory. Okay? Okay, channels. Basically, we've talked about DIMM, right? These DIMMs can be controlled by a single channel, or they can be controlled by multiple channels. In this case, I'm showing you 2 different DRAM controllers controlling 2 different DIMMs, or 2 different sets of DIMMs. You can consider multiple DIMMs over here and multiple DIMMs over here. These are independent channels in this case. Basically, some addresses get mapped to here, some addresses get mapped to here. Okay? But you can also have dependent or lockstep channels where you actually have a single memory controller controlling an even wider interface. Right? Here we have a 64-bit wide channel, two 64-bit wide channels. Instead, if you want to get 128 bits in one access, you can have a single memory controller controlling two DIMMs. Right? It's basically sending the same command to the two different DIMMs. OK? OK. So this is kind of generalizing the memory structure we're building up. Right? Basically, we started with this bank structure. And cache line is multiple columns over here. And you have rows also. And you have multiple banks within a DRAM chip. And you have multiple DRAM chips over here that are aggregated together as a rank. And you have multiple ranks. Consider these DIMMs. A DIMM can also have multiple ranks as well, as we will see. And a number of DIMMs or a number of ranks get connected to a channel that are shared by or controlled by a single memory controller. And you can have multiple channels at this level. I believe this is kind of 5-dimensional if you count the number of levels. You start with a 2-dimensional array, and then you add the rank abstraction and then the channel. And this is another way of looking at it. This is in one of your readings, so you can take a look. OK, let's do the top-down view. Any questions before? So hopefully you have a good idea of what a DRAM system looks like. Let's take a look at also from the top down. Basically, in today's processors, you actually have many channels. Two channels are very common. But remember, there's a downside of having more channels because you're adding more pins now. And you're adding more memory controllers also, so your power consumption increases. So a channel in this case consists of two DIMMs. And if you look at a DIMM, it can consist of multiple ranks. Basically, this is the front of the DIMM. This is the back of the DIMM. And you can actually have two sets of chips over here, rank 0, rank 1. And you can see that these ranks actually have different chip selects, but they share the data bus over here. And they share the address and command buses. And you have penalty switching from one rank to another. If you're accessing this rank, if the next access goes to this rank, there's a switching penalty because they actually share this bus. Now, if you look at a rank, this basically consists of chips that are controlled with the same command and address buses and supply different pieces of data. As you can see over here, this is how you get 64 bits. And if you look at a chip, it consists of multiple banks. And you can actually multiplex, basically time multiplex the data bus across these different banks. And if you break down the bank, basically you get to this 2-dimensional array that we started with. Make sense? That's the top-down view. And that brings us back to the cell. Kind of nice to think about this way. Let's take a look at how a cache block is transferred inside this hierarchy. Basically, this is a 64-byte cache block. It gets mapped to a rank. I guess you could map it across ranks, but then you run into the switching penalty if you want to get both of them. So it makes sense to map it to a single rank. If you want, and once you transfer it, what you really need to do is, this is 64 bytes, but your interface granularity is 64 bits. So you need to do multiple accesses, 8 accesses to transfer the entire cache block. So basically, this is the column 0. You get 64 bits by accessing 8 bits in each of the chips. And then you move on to the next 8 bytes, and then next 8 bytes, and then next 8 bytes. And you do it 8 times to access the 64 bytes. So it takes 8 I/O cycles to transfer. During the process, 8 columns are read sequentially. The good part is this can actually be pipelined in DRAM because everything is part of the same row. So you can actually pipeline the accesses. So you don't need to wait for an entire latency. You can actually pipeline the reads in DRAM. OK, so what are the latency components of this? I'm going through this relatively quickly because it's really easy to understand if you think about it very little. There are actually a lot of latency components to transfer a cache block, right? First of all, from the core to controller, there's some transfer time. You have to go through the cache hierarchy, right, to figure out actually you need to get to the controller. And then there's latency in the controller itself, memory controller. There's queuing and scheduling delay because there may be other requests that you need to service. And the controller converts the access to basic commands. Remember, your access is really, I want this cache block. But then the controller looks at the state of different parts of the DRAM system and says, oh, I need to transfer this request to different commands. It requires an activate, or it doesn't require an activate. Make sense? And then there's the transfer time from the controller to the DRAM itself. That's the command transfer time. And then there is the DRAM bank latency. Let me switch this to here also. And this depends on where the data is. If it's in the row buffer, it's fast. If it's not in the row buffer, you need to actually do these commands. And I'm giving you these different names. Basically, DRAM actually uses different kind of names, unfortunately. If the row is open, then you just send a column address strobe. You just send the column address, basically. It's called CAS in DRAM terminology. If the row is closed, but the array is pre-charged, you just need to send an activate command, which is the row address strobe, basically the row address, plus after that the column address. And in the worst case, if the array is already activated, it's not pre-charged, but there's a different row in the row buffer, you first need to pre-charge the array, and then send the row address strobe, and then the column address strobe. This is the worst case latency. So the latency is really variable in DRAM. The best case is the row that you're looking for is already in the row buffer. And after that, it's still not done. You need to transfer from the DRAM to the controller, and this takes the bus latency. If you look at DRAM data sheets, you'll see a bus latency timing. And after that, you need to transfer the data from the controller back into the cache hierarchy. Right? This actually takes long and long. OK, I'm going to go through this quickly because we've already covered multiple banks. But multiple banks enable concurrent DRAM accesses. And we already said that bits and address determine which bank an address resides in. And multiple independent channels serve the same purpose, basically. It gives you more concurrent DRAM accesses. But they're even better because they have separate data buses, right, if you have independent channels. This leads to increased bus bandwidth. You have more bandwidth going into your chip. And enabling more concurrency actually requires reducing the bank conflicts as well as the channel conflicts. Because even if you have multiple channels, you can actually still conflict in the channel, right? And can actually conflict in the bank. My favorite example to this is actually when I go to the gym, I use these lockers. And I always have these locker conflicts. Do you guys know what I'm talking about? What it is basically, I want to use this locker, but there's someone using the locker next to it. You can think of that as a bank. And I always get this bank conflict. Even though there are lots of lockers that are available, it somehow turns out that when I need that locker, someone else is also accessing it. That's unfortunately the nature of things. Bank conflicts happen that way too. Regardless of however many banks you may have, if the accesses happen at the same time to a single bank, well, you're out of luck. You cannot parallelize them, right? That's why a good mapping reduces the bank conflicts, but it cannot really eliminate them. So you'll have to live with it. So people have actually tried to minimize these conflicts. How do you select and randomize bank channel indices in an address? And we've already discussed this, so I'm going to go through this relatively quickly. Lower order bits have more entropy, so people usually use lower order bits. And we've also seen a similar problem as we've discussed earlier, right? This is similar to distributing the accesses such that you don't get set conflicts, right? And we've seen caches that actually hash the addresses or use randomizing hash functions by XORing the different address bits. That way, you hopefully get a better distribution of accesses to different banks. And you can study this. Basically, this is what happens if you don't have any overlapping. But this is what happens if you actually have accesses that are going to different banks. This way, you can actually start the access to one bank. And then in the next cycle, if the memory controller knows that the access goes to another bank, bank 1 into the bank 0, the memory controller can actually start the access in the other bank. And then the next cycle, it can start the access in the other bank. In the next cycle, it can start the access in the next bank. This way, you can actually saturate the data bus. Basically, the data from the first bank comes here. The data from the next bank comes in the next cycle. Next bank in the next cycle. Next bank in the next cycle. That's how you can actually parallelize access. This is an example of how you get actually how you can saturate the data bus by actually mapping data to different banks and accessing them this way. OK, multiple channels are actually even stronger, right? Because they actually have different data buses. This applies for multiple banks. But for multiple channels, you actually have separate address and data buses. So you can actually get the data from different channels concurrently. This leads to increased bandwidth, certainly. And you're going to get multiple concurrent accesses if the channels are independent. The disadvantage is it's higher cost than a single channel, because now you have more board wires and more pins from the memory controller. Any questions? OK. Address mapping, we've already seen this also, but I just want to make sure that we nail down the terminology. This is an example. You can study it on your own, but assume that you have 2 GB memory, 8 banks, 16K rows, and 2K columns per bank. And we have an 8-byte memory bus. This is what your address actually looks like if you're doing row interleaving. What does row interleaving mean? Consecutive rows of memory go to consecutive banks. Row 0 is in bank 0, row 1 in bank 1, row 2 in bank 2, ... And you can accomplish this by selecting the bank bits after the column bits. So these are the bits that specify which column in a row. And these are the bits that specify which row that you're accessing in that particular bank. And these are the bits that specify which bank that actually this row goes to. Make sense? Now, in this case, access to consecutive cache blocks are serviced in a pipeline manner. Basically, they're coming from the same bank, but you can actually send the addresses such that the bank actually sends it in a pipeline way. That's the page mode DRAM. On the other hand, if you have cache block interleaving, your address bits look like this. Basically, consecutive cache block addresses go to consecutive banks. Cache block 0 goes to bank 0, cache block 1 goes to bank 1, cache block 2 goes to bank 2. And this is how we accomplish it, basically, by selecting the bank bits such that they come after the bits that are needed to identify the cache block. Right? Basically, a cache block is 64 bytes. You chop off the bottom 6 bits, and you select the bank bits coming after that. In this case, the access to consecutive cache blocks can be serviced in parallel in the different banks. But they still need to be pipelined through the data bus, because the banks actually share the data bus. OK? So you can study this on your own. I guess what I'll do is skip the break and use it instead to distribute the exams. Is that good? And hopefully we'll be done early. OK. So bank conflicts are important, especially if you have 8 banks. Right? 8 actually is a relatively small number. So many memory controllers try to randomize the address mapping to banks such that bank conflicts are less likely. What the memory controller usually does is use something like this. Basically, instead of selecting bits directly from the physical address, they actually use a hash function to form the bank index. And this is one of the simplest hash functions you can imagine. Basically, you select these bits and XOR them with some other higher order bits over here. You can come up with many different hash functions. And remember, I mentioned one paper that discusses in a lot of detail. Bob Rao's pseudo-randomly interleaved memory paper in ISCA 1990. It basically targets the same problem. But many memory controllers today actually do this. In fact, they do even more things. They scramble the addresses for data integrity purposes also. But this is one way of minimizing the bank conflicts. Now let's take a look at the problem with multiple channels. This becomes even more complicated with multiple channels. Where do you select the channel bit? You can choose it from the top of the address. You can choose it from after the row bits. You can choose it from after the bank bits. You can choose it here. In this case, every 8 bytes, consecutive 8 bytes go to consecutive channels, right? Where are the consecutive cache blocks in these different cases? Well, you got to think. And there are actually many other choices, right? You can actually choose your channel bit from anywhere over here. Make sense? And this is one example of that also, right? Basically, you can actually, in this case, what's happening is consecutive cache blocks go to different consecutive channels in this case. In this case, a cache block is partitioned across different channels, which may or may not be a good idea, right? I guess in this case, what's happening is rows are interleaved across channels, right? But banks are coming from here. So you actually have multiple degrees of freedom in choosing the bits. And your goal in choosing these bits is actually to maximize or minimize the bank conflicts in the end. OK? So this is a complicated problem. I'm not going to ask you a question that minimize the bank conflicts, because it's a really difficult problem. But I'll tell you one thing. The virtual physical mapping actually affects this also, right? Operating system can influence where an address maps to in DRAM. So if you look at this, let's assume we have this mapping from the physical address to rows, banks, columns, and byte and bus, assuming a single channel. This is another interpretation of that physical address. Basically, it has a physical frame number. It has a page offset, assuming a 4 kilobyte page over here. And if you look at the virtual address corresponding to this, it has a 52-bit virtual page number and a page offset. So if you look at this, the virtual page number, while getting translated to physical frame number, the bits that change during that translation actually affect what bits come from, what bank this virtual page actually maps to. So if the operating system actually knows which bits are used in the physical address to determine the bank, it can actually do this mapping in such a way such that it can potentially take a virtual address and map it to bank 0, right? Assuming the operating system knows this. Right? Unfortunately, today, this information is really not communicated to the operating system. But maybe going forward, it may be a good idea, right? We've seen this before, right? Remember the page coloring? The operating system can do bank coloring in this case. The operating system can say, oh, I want these 2 applications to go to 2 different banks. So I'm going to color the banks. I have 8 banks, 8 different colors. And I'm going to allocate color 0, or red, I don't know, to this application. So for this application's virtual pages, I'm going to allocate physical frames that have bits that are all zeros in these bits. Make sense? That's the idea of coloring. That way you can partition the banks across applications, or across within an application also. You can put these data structures that happen to be present in this virtual page to this bank, and other data structures that happen to be concurrently accessed to this other bank. OK. And you can do the same thing for channels and ranks if you know which bits the channels and ranks actually map to in the physical address. So you can only do this if the bank bits are actually coming from this part, right? The part of the address that changes during translation. If the bank bits are actually coming from here, you cannot do this, right? If you're actually doing cache block interleaving, for example, if your cache block is 64 bytes, and your bank bits are actually coming here, which is cache block interleaving across different banks, then the operating system has no influence, right? OK? For that cache block. OK. OK, I think I already told you this. The operating system can perform page coloring to minimize bank conflicts and minimize inter-application interference. If the operating system determines that these 2 applications are interfering with each other a lot, for example, one application is accessing this bank heavily, and another application has memory that's mapped to that bank. It's not accessing the bank heavily, but it's getting delayed because this other application keeps accessing that bank. The operating system can say, oh, why don't I map the locations that this application is accessing to some other bank by using page coloring. OK. So there's more on reducing bank conflicts. This is a really important problem. I'm not going to cover this in more detail. But this is just to reinforce the concept. Everything looks the same, right? Internally, you have these bits going into a memory block, and you have some output. Even the bank abstraction is not correct. Internally, a bank is divided into these subarrays. So what I told you is kind of a lie, if you will. It's not a lie, but it's a good abstraction, let's say. So what I told you before is that you have this row buffer within a bank, right? Well, actually, even having a 32K long or 32,000 row bit line is too long for accessing it fast. This is really a long interconnect. So internally, a bank looks like this. It consists of multiple subarrays, each of which is about 512 rows. So you actually have 64 subarrays in this case, right? And they actually share this decoder and share the global row buffer. But what happens is, when you access a row, you really activate a row in the subarray, and you have a local row buffer to sense it. So you don't have a single row buffer for 32K rows, but you have a single row buffer for 512 rows, and you actually have 64 of these row buffers, sense amplifiers. Why? Because driving this 32K row long interconnects is too slow. So we drive only 512 row long interconnect, and we amplify it. And then we can later connect it to global bit lines to drive that out of the chip. That's a lot easier, because now you actually have a lot more drive capability if you go back to these sense amplifiers over here. Because these sense amplifiers can drive the global bit lines much better because they actually are cross-coupled inverters that are big. They're much more powerful than the simple capacitor that we have over here. That's why it's designed this way. So what I told you is the right abstraction, because these subarrays are actually not exposed to the memory controller. But if you actually want to reduce the bank conflicts even more, what you can do is you can make these subarrays a little bit more independent. Basically, you can pipeline access to these subarrays to take advantage of the fact that you have many subarrays. And then you can reduce the bank conflicts because you can actually parallelize one access that goes to this subarray with another access that goes to this subarray. It's not done today in today's DRAM chips, but if you take a look at this paper, you can get the high level of the idea. In fact, the paper that I recommended from Samsung and Intel mentions this paper, saying that this is a good idea to reduce some of the bank conflict issues that they're having. Anyway, I'm not going to talk about this in detail, but this is just to have you think that the abstractions that we have are not necessarily the same as what's implemented physically in the chip. And you can also imagine that subarray actually has smaller components, right? OK. Do I want to go into memory controllers? I guess let's stop here. We'll do what I will do in the next, hopefully, 5 minutes is distribute your exams. Any questions before we do that? No? Everything is very clear? Now you know how to design DRAM? You covered the circuits aspects of DRAM, right, in a previous course? Yes or no? Sort of? But you know the DRAM cell from a previous course, but you don't know exactly how it works. OK. So definitely do the readings, because the readings will give you insight into how it actually works internally. I know that not many courses, unfortunately, memory system kind of sits, the picture that I showed you earlier is really true in education as well. Let me go back to that picture if I can. Yeah, this thing. Because memory system kind of sits here, it's been ignored. People who teach storage focus on this. People who teach computer architecture focus on this. And as a result, there's no man's land over here. But after taking this course, hopefully you won't be in that no man's land, because this is so important. It's going to be even more important going into the future. So do those readings, the readings that I suggested. And these are actually relatively short readings. If you do read section, especially 2 of these 2 papers, you'll have a very good understanding of how the DRAM operates internally. And everything that I mentioned will be reinforced after you do these readings. OK, so let's end here, and we can distribute the exams. You want to partition the distribution?